Hello, my name is Matthew Forrest, and I'm here to speak to you on behalf of the Stevens Robotics Club, the IEEE chapter and ASME chapters here at Stevens Institute of Technology, as well as my senior design team. Here we are working towards a NASA competition to build a mining robot that will be used in lunar and Mars exploration. This endeavor is brought to us by NASA on behalf of the Artemis program, where NASA plans to get the next step in space exploration. So their idea is to start with the lunar South Pole, obtain water in the form of icy regolith, and then use that to propel human space exploration to Mars and beyond. And where do we come in this? So our involvement is a student team of multiple organizations, as I mentioned before, that we're competing in the NASA Robotics Mining Challenge Lunabotics 2020 competition. So the idea is that we're going to design an autonomous or teleoperated mining robot, excavate, store, and deliver at least 1 kilogram of icy regolith, compete against other universities, and try and be the best one there. The challenges that are presented are the obvious ones in that the robot will not be easy to build. We need to design this, build it, integrate it, and test it to make sure it's actually going to achieve what we want it to achieve. On top of this, we have a big team. Most senior design teams here at Stevens are 4 to 5 people. Our team is 12 people in addition to three other organizations. So coordinating all of this, making sure that everyone's on the same page is one of the bigger challenges. And now we're going to discuss the actual competition setup. On the screen, you'll see the mining area, which is the arena that we will be competing in. To the right, you see the list of requirements that are big key ticket items that we need to hit when we're doing the competition. So we start off with where the robot is placed. It's the right side of the arena, right by the collection bin. Its first task is to move from the right side to the left side, called the mining area. In doing this, it needs to avoid craters and rocks, and once it's in the mining area, it will begin its excavation process. Here, the robot will dig through a layer of BP1 simulant hidden beneath it. The rock will then be collected and stored in the robot before being returned to the collection bin for scoring. This is where we need to have at least 1 kilogram of the icy regolith. On top of this, we need to make sure that we are abiding by all of the requirements set forth by NASA. There is a weight requirement of 60 kilograms, it has to be less than that, and a volume requirement such that it is less than half a meter wide, half a meter tall, and a meter long. Furthermore, the robot needs to have controls in it to make sure it is autonomous or teleoperated, and that it needs to do all of this in less than 15 minutes.
The mechanical design will be made of 3 different sub-assemblies, starting off with the chassis, that is tank drive, so each side is controlled independently of the other. It will maneuver over to the mining field, and once there, the conveyor belt end effector will deploy, moving from a horizontal to a vertical position, slowly being lowered into the ground, where the conveyor belt will scoop up the material and deliver it to the storage area in the robot. In the storage area of the robot, a secondary conveyor belt will move the material from the storage area to the trough where it can be delivered for points.
So this here is a systems level electrical diagram for the various components on our rover, ranging from the main computer and the microcontroller to all of the various sensors that we will be using for localization, as well as the motors. Our team opted to use Robot Operating System, ROS, in order to run all of the software for our rover. So we can see in this diagram that we have 3 primary systems in our rover, ranging from the autonomous system, the drive system, and the mission control system.
This diagram shows how information will flow through the software system on the robot. The ROS nodes will take in input from the external sensors to create an estimated position and a map. Which will then be used to plan a path to the robot's goal, which will then be used by the motion node to traverse the robot through the arena. The team has made some progress in actually localizing the robot through the use of a visual April tag detection system. As seen in the pictures on the slide, the camera is able to detect the April tag and determine the real-world distance from the camera to the tag. The team has also made progress on the simulation front. We've been able to simulate a robot just like ours in terms of weight and mass and dimension, and get it to autonomously path plan and localize itself in an arena while building a map as it moves through the world.
And now on the screen is a project schedule up until the competition date in late May. To date, the team has secured $5,000 from the SGA, Student Government at Stevens Institute of Technology, and $1,400 from the Stevens Mechanical Engineering Department here. But we hope to garner additional funding from L3Harris to further support prototype construction, development of novel mechanisms, purchase of necessary electronic components, and to compete with a truly marvelous robot at NASA's Kennedy Space Center. Thank you.